Please press the buttons of both subscribe and like, and set the notification. The paper I am going to introduce today is this. The title is Microbially Powered Electrochemical Systems Coupled with Membrane-Based Technology for Sustainable Desalination and Efficient Wastewater Treatment. And I am a student Sung-Woo Lee, Department of Environmental and Energy Engineering, Cheonam National University. I present this thesis to you today. Modern civilization is maintained by essential components like water and energy. However, increase in population, depletion of natural resources, and increase in global warming have given rise to water and energy scarcities. By 2025, about 20% of the countries will suffer severe problems in water shortage, and there will be a lack of access to safe drinking water to about 2.7 billion people, as estimated by the United Nations. It is also predicted that 50, 114 and 52 years are the respective years for oil, coal and gas depletion times. Sustainable technologies are, therefore, the most relevant in addressing the problems of resource scarcity and environmental protection in energy-efficient wastewater treatment and wastewater generation. Microbial electrochemical technologies are evolving to collect energy using electrically active bacteria. The MESs are beneficial compared to conventional biology treatment technologies due to their various forms of energy recovery and less sludge generation. MESs mainly promote wastewater disposal and energy recovery. For systematic review, there are 4 types of MES-MTS. Microbial desalination cells, or MDCs, microbial reverse electrodialysis cells, or MRCs, microbial combustible fuel cells, or OSMFCs, and pressurized microbial modification cells, or PFMFC, as illustrated in Fig. A general MDC is rectangular and comprises 3 chambers as shown in Fig. There are several limitations to rectangular 3-chambered MDCs, like collection of chloride ions in the anode chamber and imbalance in pH between anode and cathode chambers. Many studies have suggested changes in MDC designs to overcome these limitations. Factors like hydraulic retention, or HRT, in components were also analyzed, as well as initial concentrations. Various factors have been discussed in table in comparison to different types of MDC configurations. During the early desalination phases, the consistency of energy recovery, the anodic microbial structure and desalination rate were also determined by the salt water concentration. Continue UC comparison to different types of MDC configurations. Continue UC comparison to different types of MDC configurations. A mixture of FO and MFC has been developed to provide clean water. A traditional 2MFC container design is similar to OSMFC, but instead of an IEM membrane, a FO membrane divides the chamber as shown in Fig. The OSMFC anode chamber is filled with wastewater with low conductivity, like the feed solution, and fitted with EAB electrode anode. A cathode that absorbs high levels of salt water. OSMFCs follow the same description with respect to the other MESs. The osmotic pressure between the cathode and the anode chamber produces clean water from the salt water on a FO membrane when electricity is generated through the combination of the anodic oxidizing reaction through cathode reduction with the EAB. MDC itself could not amplify the desalination process, hence MDCs combined with other membrane technologies were introduced. These membrane technologies include FO membrane technology and DD membrane technology that produced much better results than MDC alone. The DD technology was mainly used for the elimination of boron from desalinated water for better growth of plants. Microbial desalination cells were integrated with microbial electrolysis cells to produce hydrogen, simultaneously treating the wastewater and water desalination. MEDC modification is constructed by integrating MEC and MDC for COD removal and desalinating water along with hydrogen production. PFMFCs are related to as the principle of pressure filter microbial power cells, microbial electrochemical membrane reactors, and electrochemical bioreactor membrane, MFC membrane bioreactor, and UFMFCs. During most of these experiments, new architectural configurations were developed. Consequently, PFMFC generated different configurations. The FFMFC is classified into 3 main groups. Between the anode and the cathode of a MFC can be mounted a red cell stack. The MRC red stack is comprised of high and low concentration cells segregated by AEM and CEM. The first MRC reactors were fitted with a red stack and 2 modified MFC chambers. As discussed in Fig. In most previous studies, the model of the first MRC was used, and a number of MRC trials have measured major effects. The bulk of MRCs in household wastewater as the carbon source for MRCs have been used to manufacture acetate. Challenges and possible solutions in the field. MESs will become versatile through the incorporation of membrane water treatment systems and energy generation techniques, which will allow you to solve existing MES problems. Next, different studies have compared the results of MES-MTS explicitly because the product output usually is measured using multiple variables that can vary considerably or are not adequately detailed to be reported by different teams of researchers. The scaling up of MES-MT reactors and the attachment of several system units are currently considered as the possible solution. Nevertheless, most of the reactors designed in previous studies were millimeter-sized. In order to address issues currently faced by MESs can be made more robust and funded by membrane-based water therapy and energy generation technologies. But core membrane-related issues have to be resolved. Possible solutions to challenges. In addition to these critical obstacles, researchers pose several other bottlenecks in the marketing of MES-MTS. The website and the intent of the construction of materials and organic carbon supplies are linked to different factors such as reactor capacity, electrical, and membrane materials. After the quality analysis of several types of MDCs, the designs for a technically integrated MDC wastewater treatment plant were designed as illustrated in Fig to improve overall output and decrease electricity consumption. Include stacked MDC configurations in this system since sampling is easy, additional MDC units are attached to each other, and the desalination rate is required. Definition of the general process. Wastewater processing plants typically of domestic origin. 3 MDCs are used as a reverse osmosis as a pre-desalination device. The above-mentioned 2 desalination solutions can be contrasted with the most viable alternative plant with matrix checking. In order to choose the best alternative, 6 metrics will be used, including capital cost, operating costs, waste treatment efficiency, environmental impacts, and health. Solar desalination reduces the power consumption of the factory. Multi-stage solar collector-assisted desalination should receive greater exposure. Potential applications beyond desalination, electricity production, and removal of organic carbon. MDCs and OSMFCS are the primary potential application of pretreatment for desalination processes, such as RO and ED, in order to reduce their demands for electricity. In addition to uses for electricity generation and lower salinity, MES-MTS can also be used for beneficial chemical production processes. Dangerous heavy metals such as chromium and copper, and hardness in desalination chambers can be removed from the MES-MT by cathodic reduction reaction and electric ion immigration. The potential areas for MES-MTS are denitrification and nutrient recovery. ASMD-DC system that can be used to adjust the MDC structure can denitrify groundwater on site. Use electrical fields to capture anodic soil nitrate and electrochemically reduce the number of nitrates obtained from the cathode chamber. Manufacturing MDCs have had larger environmental effects. A full LCA summarized in the table showed 22.7% significance during industrial production and 58.7% during global warming operations. The cost estimation along with various other parameters like energy consumption has been discussed in table. MDC is a futuristic technology that can minimize power consumption and can act as desalination source if installed as pretreatment units during water treatment. There are various modifications carried out by integrating MDC with other membrane-based technologies to reduce the limitations observed in conventional MDC systems, which has been summarized in table. Further research on its scale-up is required on the basis of economic feasibility of the process along with environmental sustainability for commercialization of this technology. Thank you very much.